Hi everyone, I am MD Mazhar Islam from University of North Carolina at Charlotte and my advisor Dr. Ihab Al-Shai from Carnegie Mellon University. Today I will present our paper, Active Deception Framework, an Extensible Development Environment for Adaptive Cyber Deception. In modern cyber warfare, there is an asymmetry between the adversary and the defender. The defender needs to protect all susceptibilities into the infrastructure, whereas the adversary needs to find only one vulnerability to exploit. Existing attack prevention and detection techniques have several limitations. For example, the time window between discovering a vulnerability and applying patches is long enough, sometimes around 16 days to 6 months. Patching is hard as well. On average, at most 14% of the vulnerable host gets patched. Moreover, skilled attackers can easily avoid static signature-based detection. Therefore, a proactive approach must be used by the defender to break the game. Cyber deception is a promising technology to achieve this goal. Cyber deception is an intentional misrepresentation of the real system's ground truth to manipulate adversaries' course of action under the premises of the defender's rules. Deception can be used to divert adversary away from their target to false or no target. It can be used to distort adversaries' perception of the infrastructure by adding ambiguity and decoys into the network. Deception can deplete adversary by consuming their computational power to delay attack propagation. It can discover adversaries' hidden tactics and techniques by letting them run into honey environment. Deception is getting more popular. It is expected that the global cyber deception market expense will grow up to $2.3 billion by 2022. However, developing cyber deception techniques in real network is a highly complex task. It requires significant effort in implementation and network configuration management. Efficient and adaptive cyber deception requires continuous network monitoring to observe adversaries' activities, optimal planning for feasible implementation, safe deployment without breaking the integrity of the system. As a result, few deception frameworks are developed and validated in real-life operational environment. Therefore, we developed an active deception framework to build sophisticated cyber deception applications. The goal of the framework is to make deception infrastructure as a service through high-level APIs that will abstain the deception architects from intricate details of low-level deception primitives implementation, their orchestration, and their safe deployment. ADF provides an open environment for developing deception by an extensible rich API sets, a decision-making engine for optimizing deception plannings, and a controller for automated orchestration and deployment of these deception techniques. The novelty of the ADF framework is the extensible rich API sets. We have 4 sets of API. The deception APIs help to create various deception functions and applications. The sensor APIs monitor adversary activities into the network. The management API configures cyber resources such as switch, link, host to orchestrate deception operation. And the constraint APIs define the constraints to optimize honey networks such as risk, rerouting, reachability, availability constraints while deploying honey resources. These are the examples of some deception APIs. For example, Create Honey Network API will dynamically create a honey network with decoys and shadows of a given target. Create Shadow API creates an identical fingerprint of a given host in the honeypot. These are the list of other APIs. For example, Ease Host Scanning, Get Critical Links are sensor APIs to monitor adversary activities. Management APIs such as installing flow rules, blocking a particular traffic will configure the network. The constraint APIs such as overlap, can reach will help to optimize the deception planning. We developed ADF over software-defined networking. SDN provides a programmable environment over network configuration management through a centralized controller that enables comprehensive diagnosis of the observation and quick deception action responses. The following figure describes what is the strategy we use to provide active deception. For example, the sensor API monitors the adversary activity and provides feedback to the decision-making unit. The decision-making unit decided what kind of deception goal it will achieve, and the feedback goes to the planning agent. Using the constraint API, the planning agent solves and optimizes the deception planning. and find out the configuration strategy which need to be deployed. Using the management API, the configuration deployed into the network. Now we will discuss some case studies. The first one is distortion and discovery by creating honey network. The API name is create honey network. It creates a honey network with shadows and decoys of a given target to protect it from reconnaissance attack. This is the API structure. It has several parameters. The two important parameters is K anonymization and L diversity. The K anonymization places K-1 shadow host with identical fingerprint of the target. The L diversity places L-1 decoy host with fake services of the same software type but different versions or vendors. Here is an example network. If we wanted to protect the critical resource R1, the JSON structure of the API call will look like this, where the anonymization is 2 and the diversity is 3. Now assume that the critical resource R1 is running Ubuntu and it has 3 services. As the defender wants 2 anonymity and 3 diversity, which means 3 minus 1 equal to 2 diversity. That means all of these services will have at least 2 other versions. So this constraint will go to the solver, and the solver will figure out what kind of decoys and shadows we need to deploy. Now assume that the solver finds out we need to put 2 decoy, D1 and D2, and 3 shadow hosts into the network. Therefore, ADF will integrate a honey network with the existing network. This is an example how we create the shadows and decoys. For example, in our framework, we have a tool called Vagrant that actually creates the shadow host with different services. This is the nmap scanning result of an adversary. So after the honeynet creation, if the adversary scans, it will find some shadow host, including with the real host as well. The second case study is spatiotemporal mutation. The API name is spatiotemporal mutation. It changes the static view of the network by periodically mutating the static real IP addresses to short-lived virtual IP addresses. Therefore, the adversary needs to increase their probing to find the real target. This is the API structure. So H is the target list of the host that we wanted to mutate. EIP is the virtual IP or the ephemeral IP addresses. T is the lifespan, that how long the ephemeral IP will be lived, and how describes the distribution of this API, this IP list. Now, from the previous network, we wanted to protect the critical resource R1 and 2 benign user U1 and U2 through spatiotemporal mutation. So after the API calls, the ADF will create a mapping of virtual IPs and real IPs between these 3 hosts. And it will create a mapping that how this host will communicate with each other. Now let's assume that the user U1 wanted to communicate with real host R1. So the IP address of U1 is 10.0.0.1 and the IP address of R1 is 10.0.0.3. These are the real IP addresses. So the mapping says that instead of using U1's real IP 1, it will use 11 to reach critical resource R1. Therefore, a flow rule will be installed where the source is 1 and the destination is 3 will be changed to source 11. Similarly, when R1 replies back to U1, the destination will be now changed from 11 to 1. This is the actual flow rule that installed into the switches after this API get called. Now assume that the critical resource R1 try to communicate with user U1. In that case, the real IP of R1 is 3 will be used to communicate with R1 as virtual IP 7. And the following flow rule will be installed, where the destination, where the source is 3, the destination is 1, and the source IP will be changed from 3 to 7. Similarly, when U1 replies back to R1, the destination will be changed back from 7 to 3. Here is the example of the actual flow rule that installed. into the switch. The third case study is deflection by redirection. So the idea is here that after the mutation starts, all of these critical resources and the users will have the short-lived ephemeral IP addresses. Therefore, if in a reconnaissance phase, adversary collects the static IP addresses, this will no longer be validated. So if any direct probes happens, the redirect API will redirect the packet to a honey resources. For example, after the redirection API get calls, there will be following flow rules. The following flow rules will be installed into the network. The first flow rule says that any direct probing to a critical resource will be forwarded to a proxy P1. For example, the adversary A1 tried to direct probe the critical resource R1. Therefore, this packet will be redirected to the proxy P1. The proxy will then forward the packet to a decoy D1. And the decoy will send reply back to the proxy, and the proxy will forward the packet to the adversary. Therefore, the adversary will assume that he actually finds out the critical resource R1, although it is actually coming from the decoy D1. We evaluated our framework by calculating the overhead it takes while creating a honey network. For example, it takes around 3.7 seconds to create a honey network with 20 shadow and decoy hosts. We also check the ephemeral IP address creation and their mapping while creating spatiotemporal mutation. For example, a spatiotemporal mutation with 50 EIP, ADF takes 2.6 seconds to install all the necessary flows into the network. So in conclusion, we present an active deception framework that enables an open environment for developing sophisticated cyber deception applications. ADF leverage an extensive deception API that can be used to build multi-strategy deception policies. We show different case studies by developing various goal-oriented deception strategies. ADF incurs very little system overhead while providing proactive defense by deception. We plan to include more sophisticated optimization techniques such as POMDP, ZMDP in the future. We wanted to integrate various types of honey sinks such as honey files, honey web pages, honey applications, and more. And we wanted to deceive other classes of advanced persistent threats such as malware. Thank you.